So let me introduce Dániel Rákos from Rastergit, who is also sponsor of this event. So he will speak about Vulkan for us a little bit.
Yeah, thank you for the introduction. Yes, to understand our background and why are we talking about Vulkan. So I'll start with a little bit of shameless self-promotion. So I'm mainly a graphics guy, so you will hear me call kernels shaders and things like that. But at the same time, I have my colleague Mate, who's coming from the HPC and the scientific compute world. So we're trying to marry the ideas of like why Vulkan could be interesting for the compute and HPC world. So yeah, why are we talking about the graphics API? Well, it's GPU day after all. So even though like compute folks have this view of a GPU where it's mainly about having a compute units with their ALUs and cache hierarchies and memory, of course, and feeding in the kernel launches to the command processor. But as a graphics guy, I see it more like this, and this is what you have in a typical desktop GPU, even though nowadays you have GPU accelerators that look more like the previous slide. So we have all sorts of other hardware here. We have texturing units, geometry engines, rasterization engines, and even special units like DMA controllers, video decoders, encoders, motion vector estimators. So all of these are on the GPU, and that's my view of hardware. And you could use obviously these features for your visualization use cases, but because hardware is always going to be faster than software, if you find some clever ways to abuse all those pieces of hardware on your GPU, you might get some additional performance out of the hardware. But looking further, really, when we are working with GPUs, we also have to be careful about like how do we communicate with the rest of the system. We have to talk with the CPU. We have to share data with system memory. We might even talk with other devices like ISPs, sensors, other GPUs, network cards, capture cards, or even storage. So even though like when compute folks mainly focus their work on optimizing the kernels that run on those compute units, it is very important to also to like how do you interact with the rest of the system, how you feed your GPU with operations. So the current compute landscape with Vulkan is that Vulkan always had compute shaders, graphics people use them too, but the intermediate representation, the SPIR-V used by Vulkan is slightly different than the one, for example, used by OpenCL. It has a bit different capabilities and some semantic differences, obviously because the different markets need different things. In particular, another specialty of like graphics shaders versus or graphics compute shaders versus OpenCL kernels is that the precision requirements are not the same in Vulkan. That's mainly driven by graphics. So we're still talking about the same underlying hardware. So in the end, it's just a matter of having to expose all the same capabilities to be enable like proper scientific compute on an API like Vulkan. And in fact, there are various efforts happening in the ecosystem. There is a CLSPV project, which is a compiler that compiles OpenCLC to the Vulkan flavor of SPIR-V. There is CLVK, which is a runtime implementation that implements the OpenCL API on top of the Vulkan API. And even the Mesa driver stack has an OpenCL frontend, the Rusticle, that can actually run on pretty much any Gallium driver, including the Sync backend, which is a map which uses Vulkan as a backend. So there are different approaches to already run even OpenCL content on Vulkan, although like none of these are mature enough. They are more in an experimental phase at this point. So yeah, explicit, not that kind of explicit. So what is this all talking about whenever people talk about the Vulkan API, that it's an explicit API? Well, the way to think about it, and the best analogy I can come up with, is that in the traditional APIs like OpenCL, it's kind of like going to a restaurant. You look at the menu, you order something from that. The waiter will tell the cook to make it, and you will get it. You get the meal in front of you. It's pretty simple, good user experience, but you might not actually get what you were asking for. Versus like explicit APIs like Vulkan, or more like, yeah, you're at home, you have all the ingredients, you can create whatever meal you would like to, but you better know how to cook. One thing that is important to call out is that explicit API does not necessarily mean lower level API. So even though it's often coined that Vulkan and the new generation of APIs are low level, well, they contain higher level extra abstractions, many even higher than what you'll find in OpenGL and OpenCL. So it's more about being honest about what's happening behind the scenes. So practically have predictable behavior and transparency in the behavior. And in general, better application control through expressiveness. What that means is that you have a way more inputs that the application can provide to the driver in order to get the behavior that you're intending out of. You can even call it verbose, and often you will hear the example that, yeah, well, in Vulkan, it's 800 lines of code just to get a freaking triangle out on the screen. Yeah, that's true, but like with any real world application, all that boilerplate amortizes. So it's not a real issue in practice. So yeah, we will go through a couple of examples of like driver magic versus application control, traditional APIs versus explicit APIs, and things you might not even know about the behavior of your application when you're coding with an API like OpenCL. But before going there, just to understand how does a typical GPU stack look like? Well, first of all, you have your shader source or kernel source, however you want to call it. That goes through a compiler that will produce your GPU-specific ISA, which will eventually get to run on the compute unit. On the other end, you also have your API calls that's calling to the API runtime. And what the API runtime does is it will build a command buffer, which is an in-memory representation, again, specific to your target hardware, which eventually gets submitted to the kernel mode driver, which does the scheduling, does the management of the hardware. And eventually the GPU's command processor will pick up this command buffer and execute your operation. The other thing to note here is that when you're dealing with resources, you like when we talk about device memory from a GPU perspective, that could mean system memory as well as VRAM. So really, there is a part of the system memory that is made visible to the GPU, often called remote memory. And there's also the VRAM, which has a part or the wall that is also visible to the CPU. So there is this potentially bidirectional view from the two processors of the same memory. And especially for those that are visible, you also have to be careful about whether that memory is, for example, cached by the CPU, whether writes by the different processors are coherent with one another, because that can bite you in practice. We have an article on our website where we go into more details about the typical memory types that you will find on a discrete GPU. So first case study, creating a buffer. You cannot figure out anything simpler, right? You create a buffer, you get back a buffer resource. However simple it sounds, in practice, it can involve a lot of things. So first of all, the driver needs to decide which memory type to put that buffer in. It could be actual system memory, not even VRAM. And there's a lot of guesswork in that. You provide a set of inputs in your favorite API, but in the end, the driver will use heuristics and whatever to decide where to put it. Another thing is that in order to actually create an allocation, you have to do a request to the kernel mode driver to actually create that allocation. And because that's expensive, and also the number of live kernel level device memory allocations are limited by your platform for performance and other reasons, what the drivers usually do is that they allocate a larger piece of memory and sub-allocate your actual requested resource within that. And that already causes a problem. The effective real memory use of your application, it could be actually much larger than what you think based on your resources. And in general, there's just automatic management of lifetime of the created resource, which again requires the driver to make decisions for you that you may not align with for your particular application. So compared to that, in Vulkan, the way it happens is that when you create a buffer, you only get a buffer resource that does not have a memory backing, and you actually explicitly request the memory requirements of that buffer, from which you get an explicit list of compatible memory type that you can use with that resource. And if you need to, you go and ask the kernel mode driver to allocate actual physical device memory, and then associate that memory with your resource. So you manage the sub-allocation and everything. Buffer mapping, that's an even interesting one. So you would, like, the naive thought is that, like, if I map a buffer, I get a pointer back and I can directly write to that buffer. And when I unmap it, I unmap it. But that's not what really happens in traditional APIs. So first of all, if your resource is currently used in the GPU, you might even get like an unexpected synchronization happening there, where your API will completely idle the GPU and the CPU, which could be a hugely expensive hidden cost. And in the end, it may actually map the memory for real, but only if it's CPU visible, and not in use. Alternatively, it might allocate you a new piece of memory. Well, the current one is in use or not accessible by the CPU. Well, again, extra memory being used behind your back, you don't know about it, extra cost of that allocation, and potentially even involves an additional copy from the real surface to your new fake mapping for which you get back the address. Lots of hidden costs, lots of things. And the most important thing is that you don't know which one actually happens. And that's often a problem when you want to have predictable performance. Same thing goes when you unmap the buffer. It may actually not unmap it because it knows that you will map it in the next frame. So why bother? Or make, again, additional copies. And in general, at this point, the driver might even choose that, okay, now your buffer points to this new piece of memory instead of the old one. So a buffer doesn't even like one-to-one corresponds to a piece of memory, again, behind your back. So you can't even reason about things like having a fixed physical or virtual address for that resource. So you select explicit your memory types, and you can only map the memory that is actually that can be made CPU visible. So no driver magic. What happens there? It maps to CPU address space. Still, a mapping operation is not cheap, right? You have to update your CPU's page tables, which again goes to the kernel. So you want to avoid that. But in an API which guarantees that you can only map what you can really truly map, you can keep that mapping persistent. So you don't have to continually call map and unmap. You can map it once and be done with that. Another thing is that caching and coherency behavior is explicit. You are told that whether your memory is coherent or cached. Because with other APIs, you could easily run into the situation where your driver allocates you an uncached system memory allocation, and reading with the CPU from anything uncached, it's just terrible performance-wise. So no implicit synchronization, no unexpected GPU, CPU stalls. Still, one thing that's worth calling out is that copying is not necessarily evil. Like in general, you wanna copy data, right? So first of all, if your target memory is in non-CPU visible VRAM, you actually have to do a copy. There's no other way. You can't actually map that. But in general, like if you have resources that you're only intending to read and write on the GPU in between, you know, other data types, you better just upload it to VRAM. Well, of course, I'm talking about discrete GPUs with their own dedicated VRAM. But the other important thing is that you can decide to do that with a DMA engine instead of just let the driver decide what method it used for the copying. But I will talk about that in a few slides, some more. So yeah, the important thing is that it's all in the hands of the application developer. Another use case, just workload submission. Well, what simpler thing can you imagine than, yeah, having a bunch of launch kernel calls, maybe a flush somewhere, maybe a copy. But even there, a lot of surprises can happen with the traditional APIs. First of all, the driver may choose to submit at any point of time the set of commands that you accumulated, because it's again, when you issue a command, typically it only just gets recorded into a command buffer, and the actual submission to the GPU happens at a later point in time. The main reason for that is that, again, it's a kernel operation. It has its cost, so you don't want to like end up submitting a lot of small batches. And for the same reason, the driver may even choose to ignore your flush call if it decides that, yeah, you're probably doing something wrong because your workload is too small. And once again, with the copy, it's tricky, right? What do you do a copy with? Do you launch a kernel that does the copy? Do you use the DMA engine if there is one on your GPU to do the copy? You don't even know, and that has an effect on the performance of your kernel, on the overall performance of your application. So compared to that, in Vulkan, the command buffers are explicitly exposed. So the application explicitly records commands into a command buffer and then decides when to submit it, potentially multiple times. So this way you can have reusable workloads. The other thing is that the actual hardware engines, the separate graphics and compute and DMA and video coding engines are explicitly exposed as separate queues, so the application can decide what workload it submits, where and when. But because this is exposed to the application, and the application developer can also do things wrong. So first of all, it's not a good idea to have actual submissions of command buffers at a high frequency. You want to keep your submission count low. Because the more commands you put in a single command buffer, the fewer submissions you have, and then the lower cumulative submission costs you have. But that's not again, it's not a general rule. It will depend on your application. So maybe you have a small operation that you want to get done as fast as possible, and then maybe you will create a command buffer with a few commands and submit it immediately. Again, this is something that should be in the hands of the application developer, because the application developer knows its content, its use case, its scenario. Similarly with synchronization, even though you have some synchronization objects exposed in the traditional APIs, really a lot of magic happens in the background. So the driver is going to track which command buffers refer to your resource, which commands read and write to it, and even maintains associated synchronization primitives it uses, and then magically will issue at certain points some work completion signals and flushes and invalidations. each of those having costs that you may not be aware of. So yeah, traditional APIs have limited control over synchronization, and practically they tie a lot of things, like hide a lot of things behind what they call a resource or a buffer or anything, like the memory backing, the view, the way the GPU is able to access it, and all the execution control and cache control related tracking and the data. And this is simple when you think about computes. Like compute is a single stage pipeline with just the kernel, and it's a single type of access. The shader either reads or writes the buffer. But when you are looking at graphics or other interrupt cases, it gets very hairy and complicated, and even more prone to performance pitfalls unless you're going explicit. And talking about interrupt, another thing I wanted to mention, that like traditionally the APIs, when they provide interrupt with other APIs, what they do is practically allow you to import and export that other API's objects, which creates this NM API interrupt help, because practically all of your APIs that you wanted to be able to work together have to define all their connections with all the other APIs, and then you just have one missing link, and you have to jump through hoops in order to even be able to share any sort of data with another API. And the other thing is that it may involve expensive driver magic. So even when you're like sharing with one some buffer with one API and another API, you don't know what happens there. Is that memory actually shared with that API, or some magic copy happens and the copy is shared? So you really can't even reason about whether the two APIs see the exact same data, the exact same resource. And that limits the set of use cases that you can actually implement efficiently in such a model. Instead, Vulkan does not try to kid itself. The external sharing that Vulkan exposes simply exposes the underlying platform handles. So when you have like a buffer or a synchronization primitive, what really happens is that like you can export those on Windows to like a D3D resource entity handle, or on Linux DMA buff file descriptor, on Android hardware buffer, or all platforms may be able to support like bus addressable physical addresses or other sort of sharing mechanisms. The important thing here though is that there is no API interrupt help. You get the platform handle, and then any other API, an API that doesn't even know about Vulkan, is able to import that data, that synchronization primitive, according to the platform semantics. So overall, with great power comes great responsibility. So yeah, what people generally know about Vulkan is that because of its more explicit control, it allows you to extract that last 10% of performance that you have on the table with other APIs. But I think the more important thing to note about Vulkan is that it enables new use cases, enables cases where traditional APIs simply can't compete with it. Because if your application really needs to be very careful about its memory budget, if it really needs to know where it places that data, what kind of memory, what kind of coherency and caching behavior you want with it, or in general just want to have predictable performance, that you won't get hidden copies in your most time critical part of your processing if you're doing something real time or soft real time, then there's really no other option. But of course, Vulkan is also not for everybody and not for every job. Certainly not a pleasant prototyping tool because of its verbosity. But the other thing to mention is that you can easily shoot yourself in the foot, even performance-wise. So if you don't use it appropriately, you might not even get as good performance out of it as with the traditional APIs. So yeah, it's all a matter of like choosing the right tool for the right job. And I hope I managed to give a bit of a teaser of like why Vulkan could be great even to be taken advantage in the compute world. Thank you. Any questions?
Thank you for the great presentation. At the beginning, you talked a little bit about the differences between the compute and the graphics workloads. And in the recent years, there have been multiple research and applied attempts at compute, let's say, software rasterization approaches like Unreal Engines, Nanite, and similar technologies. So it seems like, and the same thing can be seen in the flexibility improvements of the graphics pipeline, like the addition of mesh shaders and other stuff. So what is your guess for the future? How long the more and more complicated graphics pipeline could hold on against the flexibility of the compute pipeline for rendering tasks?
Well, for rasterization, hardware rasterization, we remain the fastest. One can create any sort of a software rasterizer that uses compute or whatever else that uses a sort of input data set that makes it look faster than hardware rasterizers. That's being the case, like there with the Nanite and other examples. The reason is that the hardware rasterizer is not designed for sub-pixel triangles, right? The hardware rasterizer is built for, because your typical triangles will at least cover a few dozen of pixels or something along the lines. So of course, you can beat anything with yeah. But to try to answer the second part of your question, I mean, rasterizers will stay. We now have ray tracing, but rasterization is still in use. So again, it's a question of like use the best tool for your particular problems you want to solve. So if you want to render point clouds, certainly don't do it with a rasterizer.
Right, thank you.
Yeah, so thank you very much. I think I got the point from your perspective better than my perspective. So maybe it's a question to you and Mate that what do you think, how the scientific community can benefit from Vulkan? So what could be the places where I can improve my calculations using this instead of
or even some framework that is used by a lot of people, which could be GROMACS from a molecular dynamics perspective, or anything which is really well fleshed out. But in both cases, what Daniel was talking about in the traditional APIs or the higher level APIs, there is a lot of driver magic involved, which helps programmers who may not be as savvy about the underlying mechanics of how a GPU executes the code. And if the driver magic is right, then you're happy. So if you went to the restaurant and you got exactly what you wanted, then you're happy. But if the driver cannot guess what you wanted and you hit some transfer latency, which a few of my colleagues have complained about, that like even if they go to really low transfer sizes, there is a plateau under which they cannot go. With a different driver, they can. So they change to another vendor, and the other vendor could go to lower latencies because their driver magic was better. So that is where the difference lies, that in the traditional APIs, to some extent, CUDA, HIP, and those other APIs are also traditional in this sense. You can hit these plateaus that you cannot. You don't have the knobs and whistles to change, and I would expect that as a researcher, if one is using some high budget framework that is developed by a university or multiple universities or some conglomerate, then those applications will eventually move to these more explicit APIs. Whereas Daniel also mentioned that like Vulkan for prototyping is a nightmare because it takes a lot of time. So exploratory code will still benefit from the traditional APIs when someone can hack together something real fast that is 80% of the way. And if that rest 10-20% is really important because it will be run millions of times or on huge data sets, night and day, then that's where Vulkan and the explicit APIs come into play.
I would add that practically there is a certain level of complexity of your applications at which point if you're using the traditional APIs, you end up fighting with the drivers. Really, it's like getting at that behavior you intended to get out of it, knowing the hardware. And with Vulkan, you don't have to go through that trouble, but you do have that initial hill that you have to climb.
So I think it's time for the most important part of the diet of a programmer, for coffee, and maybe continue the discussion during that time.